Welcome to this lecture on microcontroller 8051 programming techniques. We'll try to build simple programs for 8051. Let us start. Program 1. Write a program to store data B7 hexadecimal into RAM memory locations 50H to 58H. So let's see this program. ORG0000H is an assembler directive actually telling the microcontroller to reset the program counter to 00. Move A hash B7H, loading B7 into the accumulator, B7 hexadecimal into accumulator. Then we have to move the accumulator contents, just B7, to memory locations starting from 50 to 58. So we can do it individually. Move 50HA means moving the B7 hexadecimal to 50H location. In the same way, we can move all the memory locations with the same content hash B7H. Move 51HA, move 52HA, move 53HA, move 54HA, move 55HA, and so on. Move 58HA are the individual instructions with which we actually load the same contents placed in the accumulator to all memory locations from 50 to 58H, and then we write end. So this is a simple program. Now let's see next. 10 8-bit numbers are stored in internal data memory. We have internal data memory in the microcontroller. There in that memory, from location 50H, there are 10 numbers, 10 8-bit numbers or 10 bytes of data in 10 memory locations starting from 50H. Write a program to increment the data. Means we have to increment the individual memory locations. So let's see the program, how we can build this program. Again, ORG0000H means to set the program counter to 0000, and then the first instruction we use is move R0 hash 50H. Means that the 50 immediate data will be moved to a register R0. So this moving data 50 to R0 is that to create a pointer with the help of R0. So R0 will be now the pointer that can be used to point towards the memory where the data is to be incremented. Then we move R3 hash 0AH. That means that we will start a counter with R3 register. We load 0A immediate data into R3. That means that it is 10. 10 is loaded in R3. Then we start a loop. Because we have to increment 10 locations, we can do it like this. So Instead of individually incrementing all memory locations one by one, we can start a loop, and the counter will decrement so that we can achieve the incrementing of memory locations individually one by one with the help of the pointer R0. In the loop we say increment at the rate R0. We increment the memory pointed by R0. Then in the second we say only INC R0, means increment only R0 contents, means to R0 must be incremented so that it points us to the next location. Then we give the jump DJNZ R3 loop 1. It will do that up to non-zero R3, जब तक R3 में कंटेंट्स जीरो नहीं हो जाते, until the R3 contents are not zero, the system will move the control to loop 1. So what it will do, that it will increment the memory, then increase the R0 contents to point to the next memory location, and again it goes into loop. How it will now the decrements is DJNZ means decrement and jump on non-zero to R3 loop. So when it is decrementing 10 times, first decrementing and then checking the jump on non-zero. So at 00 contents of register R3, what it will do, it will come out of the loop. So when it comes out of the loop, we give end. So this is the process how we can increment the memory locations, 10 memory locations. Let's see the next program. Write a program to multiply two 8-bit numbers 70H and 3AH and out the result through port 1 and port 3. Assume that the A byte is out at port 1. That means the lower byte will be A, that will be put in port 1, and the port 3 will take the higher byte of data. So let us see this program. Again ORG0000H, then move A #70H. We are moving immediate data 70 to accumulator, and again we are moving move B #3AH. Again we are moving the 3A hexadecimal into B register. Then we use the special instruction in the microcontroller 8051 mul AP for the multiplication of the contents of A register and B register. So we are multiplying 70H with 3AH, and the result, if more than FFH, then the contents will be also placed in the B register as well. The higher byte contents will go to the B register. So the A register will contain the lower byte of the result, and the B register will contain the higher byte of the result. Then to check this, to see this, that where the data multiplication is and what is the content of multiplication, we can move the data or out the data at ports P1 and P3. So we out the port 1, the accumulator contents to port 1 and out the contents of B register to port 3. So thus we have achieved. We can see these ports if we connect this to a microcontroller hardware device, then we can check on the ports the contents of the multiplication. Here we have given the AND. This is not usually a routine that in a microcontroller program we will have an AND. Generally, it is designed for the programs are designed for the embedded systems. What embedded systems are that there are certain machines which need the electronic control. What is done that the programs are written for controlling the machine, and if the machine is to be controlled, it only works with an on-off switch, and rest program is always in the microcontroller memory. So whenever we start the machine, as soon as we switch on the machine, it executes the same program again and again. So there are specific jobs in certain machines where that job is to be carried out as many times as the machine is required. So in such type of machines, this electronic part is embedded inside that machine. So if that embedded electronic microcontroller part is embedded with the machine, that gives that machine the auto control. We have so many, about 98% of all the machines available for the use in different uses. 98% of machines work on this sort of microprocessor or microcontroller automation. So we have almost all automatic machines. In those all machines we are using actually microcontrollers. Those programs actually have no end. They have a loop, and that is an infinite loop. So when once this is done, so it will again go and execute the same program again and again. If we switch off the machine, the program starts. As the RAM starts, power supply is off, so the machine is off. But when we have to start the machine again, so what is happening, that the machine starts the same program again and again. So let's move to the next program. These are all assembly language programs, and these are converted to machine code by an assembler. So we give the in every program we give the directive to the assembler through ORG about converting that program or moving the program counter to 0000 by ORG command. So let's see the next program. Write a program to compute 1 plus 2 plus 3 plus dash dash up to n. Say n is 10, so we want to compute the sum of natural numbers to 10 with the help of microcontroller programmer. So there are so many methods by which this computation can be done. One of the method is that we can use the mathematical formula, and then the same mathematical formula can be converted into an algorithm, and that algorithm can be then executed with a microcontroller program. But there's another method that we take the problem directly and use the techniques being available in the program microcontroller or microprocessor program to actually make the sum of to a particular limit. So let us see this program. So we again say the org, the assembler directive. Then we have the next n equal 10, means we start a variable n and give it is the value 10. Then we move R0 hash 00. We load the contents into R0 as 00. Initialize that R0 register is having 00 content. Then we clear E. When the accumulator is cleared, then what we do is we start a loop. The loop address is RAD. Then what we do, that we increment R0. When we increment R0, then we add this R0 to accumulator. Accumulator was 00. Now if I give an increment to R0, it will be 1. So 1 will be added to accumulator. And next what we are doing, CJNE R0 hash n RAD. This is a jump instruction, and this is called compare and jump. CJNE. Compare, what it has to compare? R0 and n. Then if they are not equal, because we are incrementing R0, n is already, we know that is 10. So when we go on incrementing R0, at one time after making 10 additions through the loop, it will be 10. So at that time this instruction will come out. This loop, the control will come out of this loop. But till then it will go to RAD and then increment R0 and add A to R0. Means what are the earlier contents? Suppose in the one loop it was 1, and then now it is incremented to 2, then accumulator is already 1, then it will add 2, and in the next it will add 3, in the next it will add 4, and so on and so forth. And at a time R0 will become equal to n. At that time the comparison will be equal, so the loop will now end and the control will come to move 40 HA. Means the accumulator contents will be moved to memory location 40H, where we have the computation of these natural numbers from 1 to 10. So at that place we can put end and see that our program is over. So let us move forward. This is the program number 5. Write a program in C. Now I'm saying that the microcontrollers cannot be only programmed in the assembly language. They can be programmed in the higher level language as well. So we write a program in C for port 1. We're using port 1 to set and reset some bits to create blinking effect. Means now I can have some hardware of some LEDs outside, and those LEDs are to be made blinking with the help of the microcontroller program. So what is to be done? We'll try to see this program. See, this is the program, very simple program. In the header file we write include register 51.h, indicating that this is microcontroller register 518051. So this is the header file for that, and then we declare void delay void. So delay is needed inside the program, because if we want to blink the LED and we are not using delay, then if we set the LED and reset the LED, the blink will not be seen, because it will blink it for a very short time of some microseconds or less. So what will be done, that we cannot see the blink. To see the blink, actually we need a delay, that for some time the LED must glow. So a delay will be required in the program. Then we move to the main program, void main, void. We start the program while 1. We are creating an infinite loop. So infinite loop will do one thing, that this program will carry on, because the LED is to be blinked and this process is to be carried forward, and it should only stop when we stop the overall power supply control. So I say I start with the main instructions at port P1 equal to 0xAA. If we write the same program in assembly language, we'll use rather only AA. But here when we are writing this program in C, in the higher level language, we give the port contents into their actual form, and we use the 0x in the beginning and then AA. The actual data is only AA. So what AA is 1010 and then again 1010. So according to this 1010, one bit will get set, the other will be 0, the other bit will get set, and the other bit will be 0, and so it will be all 8 bits of the port P1. One will be set and the other next will be reset or 0. Then I call the delay, so that this situation remains for some time. And what about the delay is that for the delay there is a program. So what delay actually is, that we try to engage the microcontroller unnecessarily for waiting. So what we do is that we start a counter, start incrementing or decrementing process, then come back. So you see that we give void delay void. It is, we are starting int ij. So two variables, integer variable is defined. Then for I is equal to 0, I less than 0xff. Again the contents are put to ff, means the counter is full. Then we go on incrementing. When we go on incrementing, the ff will go to 0 0, then until I is, the 0 is less than the 0xff, I is incremented. And again after that this process is over, we start again another process of j in the same way, j equal to 0, j is less than 0xff, then j plus plus. This process of decrementing and comparing will take some time, and as soon as this process is over, the control will come back to, then what is done, that now p1 is equal to 0x55, means again firstly what were the bits set, means 1 0 1 0 1 0 1 0, now it is 0 1 0 1 0 1 0 1 because of these content is being 5 5. So those bits which were early set are now reset. We say p1 equal to 0xff, then again calling the delay. So for some time it will be 4 bits, 1 alternate bits and 4 alternate bits as 0. Then again those bits after delay, those bits will reset. What were ones will be zeros and what were zeros will be ones. So this is a sort of, this creates a sort of blinking of LEDs. The LEDs glow and then go off for some time, and so it's a blinking process. Let's see the next one. Write a program in C for LED blinking effect. Again we can use some LEDs and blink them with a different program in C. See, include register 51h as a header file, then say set bit. This is an individual bit instruction. Set bit LED equal to P0 0. It means that port 0 bit will be set and will be called as LED. So a bit, S bit, name LED, but what is actually this bit is the port 0's 0 bit, first bit. The 0 bit of the port 0 is to be set. S bit means set bit, इस तरह से, and now we can have the second bit, S bit. LED2 equal to P0 raise 4, means the fourth bit of the P0 is named as LED2 and is set by S bit instruction. Then we again declare, these are the declarations, void delay unsigned character. Delay is to be declared here. Then we have the main program. LED equal to 0 means what was the P0 0 bit, that LED is equal to 0. Then we call the delay. What the delay is, that void delay unsigned char D. Then we start unsigned int I for D greater than 0, D plus plus. We start for I equal to 245, I less than 0, I decrement. Then for I equal to 245, I greater than 0, I minus. Then when this loop is terminated, this takes some time, and then after that it returns back the program. Then LED equal to 1, the same LED is now 1. Then we again create the delay. then we say LED 2 is 0, then again call the delay, and then say LED 2 is 1, then call again the delay, and then continue this process. So that's end of some basic programs of microcontrollers. With this we'll stop here. Thank you very much.